Yes, I don't know. Well, hello everyone, we are live. So currently looking for some material that I can discuss with you today so we can go over what we're talking about right now, which is unsteady flow. Give me 1 second and I'll work on that unless anyone can you or
is it live?
Another question.
It's not live Zoom, is it?
No, it's a record. We're in lecture 23, right?
Yeah, we did 23 today. It was like unsteady flow. And then before that, we did
lecture 20.
blood rheology.
Okay.
Okay, yeah. I'm just gonna look at the notes. I probably might have another question.
Yeah, okay. So the first thing, equation or graph that I would like to point out is relationship between it's so until okay. It's a relationship between R and R, which R is the grand cylinder. It's the distance, exact distance between the origin and the radius, which is R, big R. And it's a way of using dimension of analysis. And BD max. And all that I wanted to point out is that for an Newtonian fluid, this is the type of curve that you're gonna get. I'm bringing this up because you might get something like this somewhere. If not, my bad, but I just wanted to, this is for Newtonian fluid. And then for a usually called a Casson fluid, similar plot, but it's more like this one is called. So if I need to after
That's little R over big R?
Yes, sir.
Oh, okay.
Little R over big R, and then here we have which looks awful. That is DC or velocity in the C-axis, which is this axis, over V max. Okay. But related here is how like moving up and down changes the velocity, how the velocity changes within going from the origin to the what we call the boundaries of the vessel.
The wall.
The wall, thank you. And the relationship between that velocity and Vmax. That's what we are looking at right here. And it's a dimensionless analysis. That's it. Okay. That's it. So 15, let's see. Trying to look for the one that we were talking about in class, which was something like this. Which was like something like this. So that could be helpful. We can get the notes. 1 second.
Yeah, we just did that a little bit.
Okay.
Is it H squared on the bottom or no?
It might be.
Okay.
I'm just looking for my previous notes. Okay. Can you point there in lecture 19? I started when we looked today.
Go to 19.
Yeah, like in my thing. Just put like a little note.
Oh, I can write it.
Lecture 19, Unsteady. I remember doing that for a homework, that we were working on a way of describing time, and how time would affect the
Is that
velocity
like
profile.
Jason with the A or O?
With an A. That's just in it. Songs. Without not providing more detail, that's all that I have so far. But it can help you guys. Let's see if I can see something in the homework. Okay. So I have velocity profile. So here what we have is the velocity profile of this case channel, right? And then we have our coordinate system over here, x, y. And what we have is the velocity in the x-axis, and we have Dmax. And over here, we have 2yh. These are the relationship. But what we want to explain or look at is that this is, I'm gonna talk about it from what I have here, but in the book it's very explained. Essentially, we have different profiles that all converge to one. It's also a way of dimensional analysis. And I was saying this one. What I was saying here as well is that this slope over here, it's going to be equal to the viscoelastic velocity. My body is not the exact term. But what we're looking at there is that by the slope being greater, hence time passes. In this type of flow, we are going to get to a Newtonian fluid. That's what he was saying today. So I was saying earlier, when you start like a fluid going to a pipe, at the beginning, it's not fully developed. And what we're looking at right now over here, it's the like pain diffusion that explained in earlier lections, and that takes certain time to then become more beautiful laminar flow. This is a transient time, you can say.
Okay.
That's something that I'm pretty sure we're gonna explore later in the course. But it's just to reiterate that by having a fully developed flow, you have laminar flow or any other type of flow, it has some consistency, but before that, you don't. And by just increasing time, you're gonna get it. Okay, that's essentially it. Good, thing goes okay. Here, and my set homework, what homework are we on right now?
Number 6.
6, okay. This one doesn't make a lot of sense to you guys for now. So. Distribution.
And that's 1 on the axis.
Yes, this is a number 1. because some Vmax.
Oh, you can get up to the
Vx
max.
is equal to Vmax at this point, and in this case, 2 double y is equal to h.
And then what is this time function part?
The slope.
Okay, so it's the slope
Oh,
at different,
factors.
wait, what is t? That's time t.
Yes.
So
In that case,
a slope divided by time.
yes. What we have over there and what I don't have here, and you could look into the book, is that each of these curves are related to a specific time.
Okay.
And what you realize is that by increasing the time, you're gonna have Hamiltonian fluid. It's not necessarily part of the function. Because here what we're getting is a description between the velocity of Vmax and where we are located in the channel. Similar to what we did here, but depending,
Yeah, sorry.
depending on what initial conditions, I believe, it's how you get one or the other.
And he was, I think, I don't know if this is similar to what he was showing in class. Oh, Vx.
That's what I'm trying to look for. Go for it.
Like the Newtonian flow, which line there was most Newtonian?
The one that
The top.
is 1.
Oh, to the
The
one,
top.
yeah, the one.
Yes. Although we have here,
Because the Vx equals the Vmax. How does,
the case is different because what he did in class is that he graphed it this way. It's very different because the width divided by h, which is what I have over here, and the Vmax over Vx. And he said that this term is equal to 5.
yeah, it was, I think that he was just pulling, well, we can look at that table.
Yeah,
3 point,
that would be good actually.
here, I can pull it out.
Yeah, awesome. If I can find it too, because I feel that will be best for everyone. And just refer to what is on the textbook and just go from there. Oh. That's
The fun thing is, what do you have the book?
what?
What book do you have?
The PDF is on Canvas.
Okay, yeah, but the bad thing is, like, I don't think it lets you search.
Oh, that's possible for sure.
It's fine.
Let's try out a little bit.
This is 3.2.
Textbook. Here's the textbook, and what do you know? What file is it?
What file?
What table?
3.10.
3.10. Okay, let's try to look that up.
This is 3.10, I think.
3.10. That makes sense.
Here. Oh yeah, here. So it's page 145.
You're awesome. 145.
Okay, yeah. I don't know why I put a 5 there. That was just like, wow. This.
135.
Oh, he did. There is something that has 5 here.
143.
The velocity
145.
profile approaches within 1% of the steady state value when v times t over. So when
Go for it.
oh v. So whenever that slope divided by time, whenever the slope is equal to 5.
Okay, when it's equal to 5.
That means it says that the velocity profile is within 1% of the steady state value.
Okay.
So
let's investigate. So we know that for now we are looking at unsteady, right? Steady flow. And we know that now our velocity in x, if we are in the channel, it's going to be dependent in time and also where in the channel we are located at. Okay. And that's defined as steady state velocity and the unsteady state velocity that is dependent on time and position. Okay, we know that. What we're saying is that can you tell me what this is? That's weird.
The weird
That's the word kinematic
it's called
viscosity, right?
kinematic viscosity,
There you go.
and it's Greek nu is the letter.
Okay.
And it's
velocity
viscosity,
Yeah, what is it?
viscosity divided by density.
Okay, so mu is viscosity divided by rho, like that.
Mhm.
Awesome. What we're saying is that when this expression, so mu divided by rho times time or age is equal to 5, then our velocity is like 0.99 of
Of the Mach. Well, wait,
BSS.
yeah, it says the velocity profile approaches within 1% of the steady state value.
So this portion.
So the velocity profile. Oh, yeah,
Yeah, let's go back.
okay, so there's very little unsteady character.
There you go. There you go, my man. Yes, I was trying like, bro, I remember that. Yes, you got it.
What?
Go for it. Go for it.
I don't know, I just.
So what Paul, my gracious follower here, I was losing my mind, saying that when this ratio, this V ratio, is equal to 5, Vx is 99%, V is steady, which means is that in this expression, 99% of the contribution of the velocity is from the steady state and 1% is from the unsteady. You're genius.
Mhm.
There you go. Oof. Because this is important. Remember, like so many questions based on this. I don't know if you guys have. I'm pretty sure you haven't, because you just learned about
Wait, come
unsteady.
again?
Remember answering questions in homework or exams.
You do?
I did.
Yeah, but we haven't gotten to any of this yet, so.
So it's good that we go over this. So yeah.
So what is the difference? So we have,
So this is important, guys.
so
Okay.
what is, yeah, so steady state
Yeah.
versus Newtonian. I'm getting them confused.
Okay. So Newtonian is okay. Let's go there.
Because then, and then also laminar. Now I'm getting. He was saying,
Okay, here. Okay, so Newtonian. Ooh. Newtonian. Okay. Well, Newtonian. What that tells you is rho only.
right, okay.
Could be laminar, non-laminar. It could be unsteady, steady. The only thing that Newtonian tells you is that shear, we were talking in the channels we were saying earlier,
Oh,
is that
There-
shear in the plane y, your x direction is going to be equal to viscosity times the shear rate. That's what it tells you.
mhm.
It doesn't tell you anything about what type, it only tells you what type of liquid it is. Like for example, if it's water, but the water can be going at the velocity of light, and in that scenario, it's gonna become gas and such weird and Brownian motion and stuff, physics, you know.
Mhm.
But that's the relation it's gonna have no matter what. But if you have another liquid, like being plastics, like a songs, there's the power law, those are liquids.
Mhm.
but that's independent on velocity or anything else. Basically, velocity will tell you then how the profile is gonna be and all that, but this is what you get from Newtonian.
So
Rheology. So Newtonian,
the rheology is not dependent on the velocity?
no. We can say that the rheology is not dependent on velocity. It is dependent on the tide of liquid you have.
Okay, that's good.
That's a good question, really good question, because by having this clear, if you get a theory question thrown in there, you're gonna be able to answer. Okay, I'm done. Yeah, this,
That's
yeah,
good. And
that's it, Tony.
and then we have, so I guess the main thing is like, he was saying you could have some like
Fun, right?
huh?
We are having fun, I like that.
No, we are. A plug like flow.
Oh, sure.
What is that?
So let's say we have what? We know from our boy Reynolds, that at high velocities, we are going to have or tend to have turbulent flow. So let's say we have a really incredibly high velocity. All right. So it means that we're going to have turbulent flow. In our channel, we won't have this. That will be our velocity profile. But in this example, I don't know if water behaves this way, by the way. But what it's telling us is that if we have a Reynolds number that is big, it will be turbulent. Let's put it that way. Right. So what that means is that this velocity profile won't be like that, but rather it could be like one possible way is that we have what's called plug flow. In this case, we have a region in which all the velocity is going on the same pace, if you will. And only at the very edges, zero.
This is when the velocity is very low, or what?
No, it's very high.
Oh, when it's high.
Yeah, because at this point, so what's happening over here is that the viscoelastic forces are breaking or decelerating the liquid because of the walls. So what's going on is that the
Shear
molecules,
strut, basically, like, right?
yeah, it could be that forces, but essentially what's going on is the molecules are at the walls are stopped, are pulling. The other molecules are over here, and those molecules are pulling those molecules over here, and those and then you have this one this molecule in the right center who has the least amount of force, full force of viscoelastic force, and therefore that's the maximum velocity. And when you get to a point in which these forces are so minimal in comparison to the velocity that we are passing this liquid through, or channel, or cylinder, pipe, whatever, they don't matter. We do have some particles in the walls which are at zero because of the non-slip condition that stays, but what they can like affect the other molecules is minimal. So in that case, essentially your velocity profile becomes your average velocity in this case.
Okay, and this is the case when velocity.
If we have plug flow.
Plug flow. Oh.
And let me add that too, because I have non-plug flow and velocity side.
So what contributes to the plug flow? Is it just the velocity?
It depends. It could be velocity, essentially how quickly it's flowing the liquid. And that also take into Reynolds number, depends on the viscosity, the length of the channel, because also
a high
something.
Reynolds number is plug flow.
Sorry,
A high Reynolds number is plug flow.
it could, depends on the liquid. They're gonna tell you, but what you can do is, so when you have, what you can know is, so when you have plug flow, you have what I was describing.
It'll look like.
It will look like that. And what I was about to say is that you can have a really small vessel going at velocity v and have laminar flow and have a humongous vessel in which at this point the walls are not, or the forces of this molecules of the walls won't affect at all the actual profile of the liquid.
Okay.
So it has to do with range and how that describes the liquid, because it can vary. It can be a high velocity, it can be a really big channel, it can be both. It can be that it's very viscous, it can be that it's not viscous at all. So it depends.
Okay, so a more viscous fluid.
Would have a greater Reynolds number.
Oh, right. Wait, no, that's not right.
Huh?
Lower.
Lower.
Because yeah, the viscosity is in the denominator, right?
Let me check. Pretty sure. Let me see.
Well, this is yeah.
You're right. Yeah, viscosity is in the denominator. My bad. So for reference, Reynolds is equal to viscosity. Density. Wait, what? Density. This dynamics viscosity. I'm taking this out of Google. Density, and this is velocity and a length. Right. Kinematic viscosity. Whatever viscosity. So if it's very viscous, you're gonna have a lower range number. It could be laminar. Okay, yeah, it makes sense. Because you have more forces from the molecules of the edges that can pull the other molecules. It's very viscous.
Okay.
Very thick, like honey. Or
because the viscoelastic force is more with increased viscosity.
no, here, like when you look at this, like what's going on here is that this molecules are pulling this molecules, and this molecules are pulling this molecules. So if you have something that is very viscous, it's going to be able to cohesively attract each other, like each other molecules within each other. So this is a flow that you get with a low Reynolds that could be a big viscosity, lower density, a low velocity, or a very small characteristic length.
Oh, and the characteristic length is the radius.
It could be high, it could be the radius.
It could be the height.
Yeah, like if you're talking about channel. The channel you don't have the radius, you have two plates.
Okay.
So yes, but not exactly yes. I just don't want to confuse you. But you're correct. Right. And this type of, and that's something that is good for everyone to have, because for example, I can make a mistake saying that, I don't know, viscosity was on the denominator, but what it's best to have, that is that intuition of, okay, more or less this is what is happening, and then you go to the equation, you can understand deeper what's going on, rather just looking at the question and say, oh yeah, of course, that's Reynolds. Moving on. Yeah. because it helps with theory-based questions, for sure. See what else we have.
So, yeah, I guess, are we assuming, so what makes it unsteady state? Oh, I guess it just, at some point, it's not steady state, and then it kind of goes to steady state, is that what we're?
Not exactly. So on steady state, what it tells you is that there's an accumulation going on. And what's going in is not necessarily what's going out. That's what tells you unsteady flow. So how we are like deriving I wrote it somewhere. It's like this. It's here. The way that this unsteady velocity works is that you have unsteady component and an unsteady component. That's what makes the accumulation happen, or one of the reasons. Not necessarily this association is or relation is the right one, but mathematically it's the easiest one that you can get without getting really messy because of the like the three different integrations, like variables that we
So it would be like accumulation of liquid.
Yeah. Or not necessarily accumulation. Accumulation can be positive or negative. So you can get more liquid or less liquid, depends. But here what we're looking at is not the accumulation term, but rather how the velocity is. But yeah, it's good to have that in mind. For sure. Keep going. I mean, keep looking stuff here. Feel free to ask anything. Just want to see if I can get something else that I think might be helpful. Election 19 starts on steady. Let's go again. There. So something that I would like to clarify, just for general knowledge, is that the equation for the velocity, the final one that we derived today, it's gonna have this form. That's the equation for unsteady velocity within a channel, given the assumptions that we talked about, like the maximum velocity in the center is, the maximum velocity is in the center.
That's always assumed, right?
Correct.
Okay.
So
Because it's symmetry.
Correct. And we have the velocity of the walls is 0. And we have those two terms that I think I raised, which is like the unsteady velocity and the steady velocity. And what we have is that the final form, is going to be equal to v of x e y. Then here we have the delta p h squared over a mu l. Then we have a 32 minus 1 to the n times e to the, or you can also write this exponent. I don't really like it, but preferences. E to the negative 2 and 1. This is bracket here. 1 plus 1 to the second is I to the second pneumatic viscosity times time over h squared. Oh, here's what it is. Okay. Actually, I'm really happy that I'm writing this. And then we have 2n plus 1 to the third times pi to the third. Okay? And here we are multiplying this by a. Like this e is multiplied by a, but a, right here, because I don't have space, is the cosine of 2n plus 1 times pi times y over h. Okay? And this connection I forgot, but I just saw it. Well, you can see here, we have a bunch of parameters, like y, and whatever. But essentially and this is what it goes from. You look at here, we have that expression of this velocity, the kinematic viscosity times time divided by the height of the channel, the channel square. So we already have that right here. So a way that we can see or we can like understand this plot over here that is relating that's got to moving the lot in the x-axis divided by b max, and then the width, which is 2y, over the height of the channel, is that this is how it's going to change the velocity when we're changing time in this equation. So that each different time point, we're going to have a different velocity because it's with respect to time and position. So if you have a time equals infinity, what you're gonna get is this curve. And that's what the relationship is. It's not necessarily the slope. My apologies, it's not the slope. It's just a term within the velocity profile equation, which is the kinematic viscosity times time divided by the height squared.
Is the is that area? What is that?
Which one? Oh no, I got that's a great. That's good. I don't know.
You said it was position.
Okay.
Yeah. And it's in the exponent or is it down?
No, it's not an exponent, it's multiplying. Yeah, I just wanted to, I wrote this just to make it clear.
Yeah.
And you can ask as many questions as you want because the only point of writing this is to make it clear because so I heard some people saying that the K or whatever the cosine was here.
It was in the up numerator. It looks like it.
But it's not. It doesn't go in the exponent. It is a numerator, yes. But it doesn't go in the exponent. That's what I wanted to point out here.
Okay. And this is the steady state
Unsteady.
unsteady. Oh, this is just v of x.
Yes, sir.
Okay, so that and the whole equation is what again? This is the velocity of an unsteady state. So,
yeah, this is the velocity of an unsteady state fluid in a channel. The good thing of coming to office hours so you can ask questions, you see. Oh,
Okay, so then I'm gonna. So for the first exam, he released like a content guide.
okay.
So I was wondering if he would release that or when he would release that. So I feel like, or maybe we can just like go over topics that
Oh,
will,
let's see.
for
So,
exam two, like a topic list or
okay.
something.
I'm meeting with him tomorrow, so
Oh, okay, cool.
let me, so you said guide, topic, two, okay. That's it.
Yeah.
Okay, well, if we have something else,
That's
that's
good.
what I think.
Oh, for him. Yeah, I guess, and then exam grade, I don't know if you can do that thing. He doesn't grade it. So it
Well,
might just be like,
but I could ask more in the meeting. Sam. Lisa might need to take a picture of that and put it somewhere so I don't forget. Lisa, I need a, whatever, a reminder. Okay, if something else comes up, please let me know and we put it there.
I guess like, do you make your own practice problems or does he give them to you?
I make it.
Okay.
Yeah, that's reason they were kind of funky because I just play with numbers and they
Okay,
come
yeah,
to different places.
yeah, the book. I guess like where in the book are we gonna be?
Lexon,
Um,
lesson. Well, so far we have covered, uh, let's see, that's a good question. Let's see what we have covered so far.
we were
So
in chapter 3,
we were,
fluid motion for more than one.
let's see, like program. He's from the lecture 17, maybe? No. When do you have your test?
Oh, it's gonna be. In 2 weeks, I think. Wait.
No, but when did you have your first test?
Oh, our first one was, well, there's 2 dates, I think. Let's see, which one is it? On the 11th and 13th.
11 and 13.
Yeah, they.
So 11. So anything after that, it's probably being.
Right. So I don't think we hit, Navier-Stokes. So I think that.
So October 16. Okay, so October 16 and above.
Hmm?
October 16 and above is what we can, you guys are gonna be tested on, which is lecture 18 and
Right,
beyond.
yeah.
So the first thing that we talked about was Navier-Stokes. Let me see. So for Navier-Stokes, oh, I have a book, I think, okay. For Navier-Stokes, what we have, that's 3.4, the table,
Oh, yeah, 3.2 is the whole.
yeah, that's for any liquid. But then specifically Navier-Stokes, I think what you guys are gonna be tested more, I think. Into Navier-Stokes, where? Let me take a picture of this. Yeah, the first thing that you guys touched on was Navier-Stokes. Then
I don't have a lot of stuff for lecture 18.
soak supply, which is basically getting the equations, these equations, I mean. There's this over here. Basically, these equations, you get different assumptions, and then what you do is that you start, for example, if we say that it's not a pressure driven flow, we can go ahead and cancel this. And if in this case we're talking about unsteady, so the bx over delta t won't be affected. And then you go, okay, my flow is going in the x direction. I mean, it's going in the x direction, but it's not changing with respect to x. And then you start like canceling the terms until you end up with an expression that resembles your set of assumptions. Or,
yeah, that's the Navier-Stokes. Okay.
Yeah, it's not results.
Yeah.
You cannot see it.
That's good.
That's okay?
Yeah.
Okay, cool. That's not results. Let's see what else we have.
Then we got laminar and turbulent. No.
Lecture 19.
So Reynolds number, like, what kind of questions are gonna be like? Is he gonna have us calculate Reynolds number?
You could, definitely.
Do we have to memorize that?
I will. I will memorize the question for Reynolds number. It's like,
Oh, yeah, and then, yeah, it looks like, oh, see what is it? Characteristic length.
it's good that you know how to,
See, it's confusing for the rectangular channel.
yes, because it's h over 2, right?
No, it's 2 times the width times the height divided by the width plus the height.
Yes. Yes, remember that. Let me write it down right here.
That's a
So
lot.
I know it's not beautiful. I know.
That's a
Hopefully
lot.
I can solve them to add that in the equation sheet. Let's see.
Oh, yeah.
What is it?
Oh, it's the characteristic length for rectangular channel. Basically, it's technically
Okay. Can you recite it for me, my friend?
L equals 2 times W times H divided by
Like that?
no,
No, it makes sense.
WH, yeah, divided by W plus H. So it's basically the cross-sectional area and then the perimeter is on the bottom.
Yes. Yes.
And that's what he said 4 times for any irregular conduit, it's like 4 times the cross-sectional area divided by the perimeter.
Oh, okay. This is for a channel, guys.
But I don't know where the 4 comes from.
And then we have the characteristic length of, you said any regular?
It says you use the hydraulic diameter, which is basically the area fluid that the area that the fluid is in contact with.
So area fluid is in contact with.
But
Okay.
it should be, yeah, the area divided by the perimeter. I don't know why. The area divided by the perimeter. See, it doesn't make any sense. And then you multiply it by 4.
Well,
It's probably in the book somewhere, but like I don't.
yeah,
Hopefully we're not testing on that. Like
yeah. But if I were you, I would
memorize.
take a little slice of your brain and would put that in. Because I'm pretty sure you don't want to not be able to answer a test just because you don't know that. Yeah. I'll get like a lot of points deducted.
Really?
I don't know. I'm just guessing. I'm not the grader. I'm your friend. I'm here to support you and make you a better person, hopefully.
Yes.
And we know that Reynolds number, right again, just never a bad thing, is over viscosity, density, we have average velocity and characteristic length. Sweet. We know that if the Reynolds is less than 2100, laminar. If the Reynolds is greater than 4000, we have turbulent flow. Right. Yeah. And anything between is transient. And what that means is that depending on the liquid, you can have a liquid that is, I don't know, 3800 and be laminar. Or you can have a liquid that is 2200 and it's already turbulent. So that depends on the liquid. That because you have Reynolds, 4000, 2100. But it's here, it's here, turbulent, and here's the trans. And depending on the transitional, yeah, that's actually transition, the actual word. Depending on the liquid, getting closer to, you can get closer to 4000 before getting turbulent, or way and actually just about 2100 and be turbulent. So it depends. Okay, that's Reynolds in a nutshell.
So what is the units for like rent? It's supposed to be unitless?
It's unitless, yes.
Okay, so it just, you just kind of want everything in meters and. Wait,
You put everything in 1 year. You can put everything in the middle and meters, so they cancel out. And then you,
viscosity is what?
oh, let's discuss it. I don't know. I don't remember. But you can definitely go and see. Let me see real quick.
Meters is
Oh
squared.
my God, it's Dave.
What, did it not?
No, it's recording, but I forgot to stop sharing. I was talking about was this, like channel is characteristic length. This characteristic length for an irregular, which is basically the area divided by the perimeter times 4. We're talking about Reynolds, that is when it's below 2100, it's laminar. When it's above 4000, it's turbulent, and the mu is transitional. And depending on the liquid, it will be more turbulent or more laminar in this place. So if it's closer to 4000, there are liquids that can definitely be laminar at 3800, for example, but there are some that that's what we're talking about. And now we're going to discuss. We're discussing that Reynolds is unitless, and now we're looking at is what are the units for viscosity. Really cool. Units for viscosity. Really, it's taking me so long. I'm just not finding. Okay, it's newtons per second over meters squared. Then we know that newtons is the viscosity, like the units. We know that newtons is the units of force, which is mass times acceleration over meters second, and then we know that it's mass velocity over time times time over meters squared. But yeah, that's the units of viscosity. And here you could have like mass grams, acceleration in centimeters per second, and depending on that, this in that case, this meters per second should be like centimeters per second. So it depends if you split it up with them. Usually we're not talking about meters, we're talking about centimeters or nanometers. So, so what you could have in our case would be like grams times centimeters over second squared times centimeters, so they cancel out, over centimeters squared, something like that.
Yeah, I think, yeah. I mean, I just gonna plug and chug for the
Yeah,
Reynolds number really, but I'll just probably make sure everything's in meters.
give me meters, centimeters, like whatever unit you get in the problem, use that unit and convert everything to it.
Yeah.
Like make sure that they cancel out. Okay. Well, a relationship that is good that you guys don't forget is, I mean, erase here. Oh, yeah. Okay. Now the volumetric flow rate is equal to delta P over R. Talked about that today. We know that R is the resistance well. No, this not the actual radius in this case. Something that I have to ask myself. Volumetric flow. So flow. Well, it's equal to delta E over R. So I want to know what the resistance really is. Not clear on that. Something that we know is the for Poiseuille's law, the volumetric flow rate going to be equal to delta P by R squared. In this case, this is the radius of the channel over A viscosity length. Okay. That's it for now. session is over. Please, if you have any questions, contact me, and I have seen this morning that some people have, and I didn't reply to them. I'm so sorry. Please, if you need me, as I put in my slides, the beginning of the semester, contact me in different places. I know it can be annoying, but my apologies. I sometimes don't check Ruby that often. So if you can, like, send me a message, you feel more than welcome. Call me, send me an email. Feel free to do so, so I can reach out and help you guys. But yeah, sometimes that's on me. I need to be more constant on my Ruby checking. But yeah, go Gators.